we've talked about what random variables are and what discrete random variables are, but now let's talk about how we find descriptive statistics for a discrete probability distribution. So how do we do things like find the average value? And there are a lot of things we might want to ask when we're working with a discrete probability distribution. So if we're rolling a die a bunch of times, you might want to know what the average value would be, or what would we expect the average value to be if we roll a die a whole bunch of times. Or if we're playing a gambling game, you might want to know, would I expect to win money or lose money, and how spread out are the values? Those are the kinds of things that we want to answer. So in this investigation here, there's some data from the US Census, and they found the number of households of different sizes. And it only tells us, for different household sizes, what the probability of getting a household of that size was. And so it's not telling us how many of each household size there was. And I want you to think about, if you look at this image or this little table here, what was the average household size in the United States in 2020? And I'll say that that is not a question that can be exactly answered with the data that I've given you here. With this table, because this isn't a household size of 3, but because it's 3 or more, you won't be able to exactly answer this question about the average just based on the table and the image. But I want you to maybe pause and think about how you would estimate it. Where would you estimate the average household size to be based on this information? And it can be a rough estimate, but try to think about how you would estimate it. So I'm going to say a few things about how I would estimate this. And to make this a little bit simpler, I'm going to ignore the or more, the 3 or more. I'm just going to think about that being 3. So I'm just going to pretend it's 3 and talk about how I would estimate it in that case, just to give us an idea of what's going on. So if 1, 2, and 3 member household sizes were equally likely, so if all these options of having 1 member, 2 members, or 3 members, I'm not going to think about more than 3. If these options were equally likely, let's think about first what we would do there. So if they were all equally likely, then it would just be taking the average of these 3 numbers. And I would do 1 plus 2 plus 3 divided by the number that there are, which is 3. And this would be 6 over 3, which is 2. So if they were all equally likely and I just took the average of the numbers, I would get 2. But what you might have noticed in this example is these probabilities are not the same. These things are not all equally likely. In fact, the highest likelihood is that we're in this biggest category of having 3 members, or 3 or more technically, but we're just pretending this is 3. So in my image, that's the probability that's biggest. And so if I'm thinking about the average, it looks like 2 members is also more likely than 1. And so if I was going to try to guess, I would guess that the average is somewhere between 2 and 3. And so really, what we want to do, instead of thinking about these as all being equally likely, what I would do is say, okay, 1 member, the probability of that happening is 0.29. 2 members, the probability of that happening is 0.35, and 3 members is 0.36. And so I would take each possible number and multiply by its probability. And this is actually the same thing that we were doing above when we assumed they were equally likely and we were taking the average. When we're taking an average, if I look at this fraction I have over here, this would be the same as doing 1 times a third plus 2 times a third plus 3 times a third. Our average formula is really doing this, and we have that 3 in the denominator because there were 3 things, and this is really saying they're all equally likely, whereas now we have these other probabilities because these numbers are not equally likely. So if we plug these into Excel, plug this formula in, 1 times its probability plus 2 times its probability plus 3 times its probability, we will get something a little bit bigger than 2. I believe this is about 2.07. And so sure enough, we didn't get exactly 2, we got something a little bit bigger because the probabilities of 2 and 3 were higher than 1, and that was pulling our average to be a little bit bigger. And so in general, this average that we just found, or mean, is called the expected value of our discrete probability distribution, and it's the weighted average of all outcomes of the random variable. So I know this formula looks complicated. This Greek letter here is mu for our mean or average. And what this is saying is that we take each possible x value, each of our possible values of our discrete random variable, we multiply each one by its probability, and then this Greek letter sigma means add them all up. So we start at the first one and add up to n, however many we have, we add all of those up, which is exactly what we did in this last little investigation. And that expected value, if we're dealing with money, then we call that an expected monetary value. And this is really useful. So if you were playing a gambling game, something that is good to know is the expected monetary value if you were to play the game a whole bunch of times. So if I'm playing a certain game 100 times, I want to know, on average, would I be expected to win money or lose money? What would that average value be? And we could also talk about the variance and standard deviation of our discrete distribution. And it measures the same thing that we talked about before with variance and standard deviation. Essentially, it's saying something about how spread out those values are around the mean. And now we're going to need to use this formula because we don't have a list of values. We just have the probabilities of each value. And so we're going to have to use this formula to find variance. And then once we find variance, we can take the square root to get the standard deviation. And that's something we'll see how to do in the next exercise. So let's just look at this formula. We're taking each x, subtracting the mean, taking that whole thing, squaring it, and multiplying by the probability. And then we add all of those up. So in exercise 2 here, it says that this table shows the discrete probability distribution for the number of bedrooms per house in a certain community. So in this community, apparently there are only 3, 4, 5, and 6 bedroom homes. Apparently there are none smaller or bigger than that. And we have the probabilities of each of those. And so the first thing that we want to do is determine the missing probability for this 6 bedroom house. And then we want to find the mean, the standard deviation, and the variance. So let's start finding that missing value. Well, all of the probabilities have to add up to 1, so we could figure out what the other 3 numbers add up to and subtract that total from 1. So here, all the other probabilities were 0.23, 0.57, and 0.14. We know that everything has to add up to 1, so that the one we're missing, if we do 1 minus all of that other stuff, that should give us the one that we're missing. So let's see, 0.23 plus 0.57, that would be 0.8, and then if we add 0.14, that would be 0.94. So if we do 1 minus that sum, this would be 0.06. So now we know that that missing value is 0.06, and we want to find the mean and the standard deviation, and there's this link to an Excel file that's set up nicely for us to find the variance and standard deviation. So let's open that up. So in this Excel file, we see this 0.06 that we just found. If we had wanted to do that in Excel, we could do equals 1 minus the sum of those other probabilities, and that would give us 0.06. So now we want to find the mean, which the Greek letter for that is mu, and this is the thing we call the expected value. So we want to take each of our x's and multiply by the probability, and we want to do that for each pair and add them all up. So we'll have 3 times its probability, plus 4 times its probability, plus 5 times its probability, plus 6 times its probability. Great, and we could type these all in by hand, but in general, we want to click on the values in Excel so that we don't risk rounding until the very end. So our expected value is 4.03. And there is a faster way that we can do this, since what we were doing in that formula is we were taking products of all the pairs and then taking the sum of those products. We can use the formula sum product, and we can highlight our x's and then our probabilities, and that will calculate the same thing that we just did. So this will also be 4.03. So our mu, our mean, is 4.03, and that's the same for this whole problem. So if we now want to find the standard deviation, what we should do first is find the variance. And the variance is the sum of these values in column F. And so this is just having us calculate them kind of piece by piece in this table. So if I want to do x minus mu, I would take my x minus my mu, my mean, and I want to do that for each value, and so I can drag this down. Next, I want to take those x minus mu values and square them, and I want to do that for each one, so I can drag this down. And then finally, I want to take the x minus mu and multiply by the probability for that x. And so again, I want to do this for each of my values, so I drag this down, and then my variance, my what we call sigma squared, is what I will get if I add all of those values up, all of those x minus the mu squared times the probability values. And we could have done this all in one step, but it's easy to mix up parentheses, and so I think it's good to do in pieces like this. If we had wanted to do this all in one step, let's see, I probably first would want to calculate these x minus the mu squared times the probability, but I could skip what I have in columns D and E if I did, let's see, I would want x minus the mean squared times the probability. I could jump straight to calculating that for each x and drag that down. That will get exactly the same thing. And then for the variance, I would add them up. So there's my variance. Now I want the standard deviation, which is sigma. And so once I have the variance, to find the standard deviation, I want to take the square root of the variance. So I would do SQRT of the variance. And that gives me the standard deviation. So this gives me some sense of how spread out my values are. And if you want to see these steps in an Excel file, that's on the online notes. There's a solutions Excel file where you can click through these for yourself. But I think it helps to kind of have this table with these steps to calculate the variance. And then once you have the variance, you're ready to find the standard deviation. Now let's do one more problem where we calculate the expected value or average for one of these discrete probability distributions. So number 4 here, it says Toys R Us manufactures and sells t-shirts for sporting events, and it's providing shirts for an upcoming tournament. And each shirt will cost $9 to produce and will be sold for $18. And then if they have any shirts that are unsold at the end of the tournament, they can be sold for $5 a piece in the near future. So they'll still be losing some money on those, but they can at least get some of that cost to produce them back. And they are assuming that the demand for the shirts will either be 500, 1,000, 1,500, or 2,000 shirts. And they've also estimated that the probabilities of each of these sales will be 15%, 20%, or 25%, or 40%. And we want to determine the expected monetary value of this project if they choose to print 1,500 shirts. And they've given us an Excel file that we can use. So they've already decided we're going to print 1,500 shirts, and we want to find the expected value of this project. We want to know if they expect to make money or lose money, and if they expect to make or lose money, how much they should expect to make or lose, if they were going to do this a whole bunch of times in this situation. So let's open this Excel file. So we have this summary of the problem here, and to find the expected value, we really want to know the profit in each demand scenario. And once we have the profits, we have the probabilities of those, and we can use those two columns to find our expected value. But to do that, we first have to figure out the profit in each case. So let's start in this situation where the demand is 500 shirts. So we have this kind of fixed cost up front. So we're producing 1,500 shirts, and each shirt costs $9 to produce. So we're making 1,500 of them, and so we'd multiply by 9 to get the cost of the shirts that they plan on making. That's a fixed cost. We're doing that no matter what. Now, let's go to profit here. So if the demand is 500 shirts, well, let's first think about the money that we'll make. So 500 people will be buying shirts, and they're selling each of those shirts for $18. So that's the money that we will be bringing in. So that's our revenue. But we had this fixed cost of $13,500 that it took to print the shirts or make the shirts. So that means that we have to subtract that $13,500. But we will also have some shirts left over. If the demand was only 500 and we printed 1,500, we will have 1,000 shirts left over that we can sell in the future for $5 a piece to kind of recoup some of that money. So in this situation, our profit would be $500. Now, let's see how that changes if the demand is 1,000 shirts. So I'm going to copy that formula and put it down here and see how it changes. So now I will be selling 1,000 of those shirts at full price. I still have the fixed cost, and now there will only be 500 left to sell at the reduced $5 price in the future. And so we'll do the same kind of thing for these other demands. In this 1,500 demand situation, I sell 1,500 of the shirts at full price. I still subtract that 13,500, and in this case, I don't have any shirts left over to sell at the reduced $5 price. And if the demand is 2,000, well, I didn't print 2,000 shirts. I only have 1,500 to sell at that full price. And so I just will have 500 maybe unhappy people that they couldn't buy one, but this formula will be exactly the same as it was when the demand was 1,500. I just could have sold more if I had more, but I don't. So these are the profits in those different demand scenarios. So now, if we want to find our expected value, or our expected monetary value, we would take 500 times its probability, plus 7,000 times its probability, and so on. Or we could use this sum product formula and highlight our profits and our probabilities. And this will give us $10,250. And so that tells us if we were to make shirts for tournaments like this, where the probabilities for these demands were what we had here, if we did this a whole bunch of times, on average, we would expect to make about $10,250, which is great. that doesn't necessarily mean that any one time of doing this, that this is the amount that we would make. It means if I did this a whole bunch of times, so if I'm this company that prints shirts for tournaments like this, then this is how much I would expect to make on average in the long run.